if you go with the random files and you bring those two operators, you can see what the guys actually. No, I see. So that's what we're able to figure out.
All right. Brian, can you type your name in the chat channel? Because there are several Brians in this class. I just need to know which Brian. Thank you. All right, it is 5:30 and I am getting started. So we are going to talk about branching or jumping, or go-tos, today. So it's going to be more or less a continuation of what we have been talking about, except this is a different type of instruction. All right, so we got one more person. Okay, there we go. All right, so to the people who are participating remotely, I want to remind again, there's an allowance of 3 remote participation. So I am keeping track of all of that. So make sure that we do not exceed the 3 allowances, because beyond that, it will count as absences. I will still let people in, but it will count as absences. And the 4th absence is going to be considered excessive. So I just want to make sure that is clear. And people don't accidentally think about this class as a hybrid class, because it is not. All right, so we're going to continue with our discussion. And I got all the topics in Joplin already. Okay. So this is an outline of what we're going to talk about in today's lecture, or what I'll be demonstrating in today's lecture. And it is also what you need to know for the lab today. Yes, there is a lab today. So the first one I'm going to talk about is the jmpi instruction, which, in RTL encryption, RTL stands for Register Transfer Language. Okay, it's a way to describe what is happening inside the processor. So in RTL description, it is PC gets whatever PC is pointing to. The program counter is getting whatever the program counter is pointing to. So we'll talk about that. I will go into LogicSim and basically show what is happening, how things are connected in the processor. And then we'll segue a little bit to talk about the flags in the AM, which we have already talked about a little bit. So we will do that. All right, so I'm going to let one more person in. And I'm going to have to repeat that again, because these people come in a little bit late. If you're participating online, there is a limit of 3 participation allowances. So beyond the 3, it will start to count as absences. And then the 4th absence is going to be considered excessive. And then at that point, people may be dropped from this class. I just want to make it very clear, because I think some people might have reached the limit of 3 already. So I just want to make it very clear so that nothing comes as a surprise. All right, so getting back to flags. So we're going to talk about the flags in the AMU. Other than the Z flag, the other flags we have talked about already when we talked about binary comparison, which is based on binary subtraction. And then we will go back to talk about JCI and the other conditional branch instructions. So jmpi is unconditional. Every single time you execute a jmpi instruction, it will continue execution at the location that you specify. But JCI, JZI, JOI, JSI, and JLI, those are conditional branches, which means, well, depending on whether a flag is a 1 or a 0, it might go to a certain place that you specify, or it might just continue to execute with whatever is right next to the J conditional branch instruction. So those are a little bit interesting, and the mechanism to do it is also a little bit interesting. So we'll get to that probably at the last portion of today's class. All right, so are there any questions before I get started with these particular topics? No specific questions? Okay, all right. So I am going to turn off the stage light because this way the contrast of the screen is a little bit better. Does it matter? Does it change? Not noticeably, I guess. Okay. Okay, all right. I'll just put it this way. I don't like to be in the spotlight, so I like those lights to be off. All right, so we'll go ahead and talk about the jmpi instruction first. And the first thing we typically do is to go to the opcode table because we want to find out what is the opcode of jmpi. So jmpi is right here. As you can see on column C, jmpi is indeed described as PC gets whatever the program counter itself is pointing to. The name is jump with immediate destination, which means you have to give it the destination. The destination itself has to be resolvable by assembly time. The assembler has to be able to figure out what number, what location you want it to go to. Other than that, this is one of those things that has no XXYY because it does not depend on any registers. So it is a very simple 4-0. 0, 1, 0, 0 in binary is 4 in hexadecimal, and then 0, 0, 0, 0 in binary is 0 in hexadecimal. So therefore we have 4-0. All right, so what we'll do next is I can show you a very simple program. Not this one, but let me see. I want to zoom out just a little bit because I changed the resolution of the screen. Oh, actually, I need to do something differently because the zoom is from here. It is not from the browser. There we go. And I should be going back into the source tab. So now I'm going to start the program with a no-op instruction. And then I have a jmpi to location 0. In other words, I have just written myself a infinite loop. It is not the tightest possible loop. If I want the tightest possible loop, I would have written jmpi 0 instead of the no-op. Because the no-op is taking 1 byte in the entire program. So the jmpi back to location 0 is actually not the tightest possible loop. But I'm going to run this program, and I want to do the assemble first, by hand. No-op has an opcode of what? 0, 0, very good. And then jmpi itself, the opcode has an opcode of what we just saw earlier, which is 40, very good. And then the extra 0, which is the immediate operand, is going to up another byte, which is just 0, 0. So that's what this program is going to look like. There are no halt instruction here in this case. So I switch to Logic Sim. And since I changed the resolution of the projector, I'm going to have to change the zoom ratio. All right, so we go into RAM and we have to go to edit content because it is not starting from location 0, 0. So we can kind of poke. This is called poking a program in because in BASIC, BASIC as a programming language, there is a statement called poke, which allows you to place a specific value to a specific location in memory. And that's how, in the earlier days, how people integrate assembly language subroutines into a higher level programming language. So there's certain things can be done with super high efficiency, but the rest of the program is easy to write because it is in a high level programming language. So location 0, 0 is fine the way it is because it is specifying the no-op instruction. The next one is going to be the 40, which is our jmpi instruction. And then the next one is 00, and that is fine too, because we want to specify that we want to branch to location 00. Okay, so we're doing okay so far in terms of how I specified the opcode in the program, and even without using the assembler. Now, if you're curious and want to confirm, you can always switch to the assembler, and then okay, not that one. Oh. There's my, there we go. Okay, so you can now switch to the assemble view, and you can see how the first byte is a 00, the next byte is a 40, and then the last byte is also a 00. We can also go to RAM file. Okay, RAM file just spells out everything in RAM, and we see our 00, 40, and 00. Everything is also in hexadecimal. So this way we can confirm that my program that was assembled by hand is indeed okay. It is correct. All right, so we now can switch back to Logisim. Oh, not the editor, but we want to switch back to the main screen here. And I forgot to do one thing. I forgot to do the reset first. So Control R. Well, it's okay. I just need to change that one location to 40, and we're all good to go. So I'm going to fast forward, to until we get to the execute cycle of the jmpi instruction, because the no instruction doesn't do a single thing useful. And we have talked about the fetch, decode, and execute cycles quite a few times already. Okay, in 2 class meetings, we have already kind of talked about that. So today, I'm not going to talk about that too much. And instead, we'll focus on the mechanism of the branch instruction. So that means I have to keep an eye on the program counter, this guy here, because when it is 0, 2, then I have to be careful. Now, why not 0, 1? That is why, okay, location 0, 1 has the opcode of the jump. Location 0, 2 has the specification of where I want to jump to. So why do I wait until the program counter is 0, 2? Then I go like, okay, now I have to slow down. It has to do with the ordering of things, okay? Something happens between the fetch cycle and the execute cycle. What happens between those 2 cycles that, go ahead. No, decode, yes, decode is between those. So let me rephrase the question. What happens between fetch and decode? The PC increments, exactly. So by the time I decode, the PC is already moved on to the next location already, which in this case is going to be location 0, 2. So very good. Okay, that's very good observation. Because this allows us to kind of control the relatively quickly until we get to see that the program counter is 0, 2. So we'll focus on this thing here. By the time it gets to 0, 2, we'll slow down. So here we go. Control T, Control T, Control T, Control T, Control T, Control T, Control T. Now we need to slow down, okay? Because we have just incremented the program counter to 0, 2. And we are about to have what kind of an edge? Can you visually see what is the next edge if I Control T again? Now the falling edge, which is going to be, we are done decoding at this point. Actually, I take it back. We are just about to decode because you can see how the microcode pointer is at location 001. And a falling edge, while the microcode pointer is 001, is decode. So if I Control T again, I would expect the microcode pointer to become not 002, 400, because that's the whole idea of decoding, where the opcode becomes the most significant 2 digits of the microcode pointer, with a fixed 0 as the least significant digit in the microcode pointer. Okay, so there we go, Control T, and now the ROM is addressing location 400. So this 1F80006 is presented to the data port of ROM, which in return is telling us, okay, connect this thing over here and connect this thing over here. Oh, by the way, we want to enable this thing to be updated, blah, 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 and so on. Okay, so we're going to take a quick look at what is happening here. So we look at RAM, and RAM cell is on. It is a 1. So that means, I have to automatically ask the next question, which is, are we reading or writing? We are reading because RAM load is a 1. Very good. Then we have to ask 2 additional questions, which is, who is specifying this location to read from? And what are we going to do with the data? So those are the 2 follow-up questions. So we'll answer the first question first, which is, who is controlling the A port of RAM? So as usual, we just have to track it back 1 step at a time. It goes all the way back to the output of this multiplexer. This multiplexer has a select of 1. So now we have to track down input 1, and input 1 comes from the program counter itself. So the Q port of the program counter is the output of the register program counter. So that means we are simply using the content or the value of the program counter to determine which location of RAM we should be reading from. Next question, okay? If I'm reading from RAM, most likely I'm going to update something with that content. The question is what? Well, by looking at the program counter and knowing that PCEN is already a 1, it's sort of answered the question already, but we still want to confirm that, okay? We still want to confirm that the D port of the program counter is indeed connected to the D port of RAM, okay? Because it's not automatic, okay? We cannot just make that assumption. So we'll go ahead and just trace our way back 1 step at a time. So this particular node connects to the output of a multiplexer. The multiplexer is having a 1 as the select. This time, we want to be a little bit more detail-oriented and find out why PCMux is a 1. So the question is, why is PCMux a 1? So some people may say, isn't that one of the 26 outputs of ROM, and we just decided to turn on your PCMux for this particular microcode slice? The answer is no. PCMux does not come from ROM directly. Okay, so now we have to track down where is PCMux? Why is it a 1? So if you're doing this the first time, it's going to be a little bit, it will take some time. But since I've done this many, many times, and I actually made this design to begin with, this is PCMux. Okay, this is PCMux itself. It is the output of a multiplexer, this particular multiplexer here. Okay. So if you're looking at the output of a multiplexer, then the natural question to ask is, which input is it connected to? So to know which input connects to PCMux, to give it a value of 1, then we hook this Y here. PCMux has this funny name because it is a multiplexer where the output controls another multiplexer. So it's kind of like multiplexer squared. Okay, so PCMux, which is directly coming out of the data port of ROM, has a value of 111. So that means it is using input 7, 111, to connect to the output. This is the reason why PCMux is a 1. Are we doing okay so far with this? Now you might ask, but why do we have to go through all this trouble? Why not just have the ROM to specify PCMux directly and be done with it? Well, the answer to that question will be answered later because the mechanism of our conditional branch instruction relies on this particular multiplexer. Okay, so we'll see why we have PCMux, to determine PCMux instead of having PCMux directly coming out of the data port of ROM. Okay, so now that we got that question kind of answered, then we look at this and go like, okay, we have to track down input 1, and then it connects to another multiplexer. This is a selection of 1, so we have to track down input 1, and this time we connect all the way back to the data port of RAM. So this way we confirmed the RTL description, where PC is updated by the location that it points to. Yep, go ahead.
Sorry to jump back a tiny bit, but you said PCMux is being controlled by ROM.
Yes.
ROM there's a microcode slice that's turning on.
Yep.
You're saying about months.
That is correct.
Thank you.
So you can confirm that by clicking on PC MuxMux in Logisim and then see what is highlighted. And you can see that this wire is highlighted. So it is basically bit 17 to bit 19 of microcode data, which itself is corresponding to bit 3 to bit 23 coming out of ROM. I mean, how I hierarchically, split, the output of ROM is not really important. The key is, those 3 bits came out of the data port of ROM. Okay. All right. So now that we know what is going on here, the next question is looking at RAM as it is right now with location 0 to addressed, and looking at the program counter as it is right now, the next cycle or the next edge is a rising edge, which means we are indeed going to update the program counter at this point. So the question is, what do you expect to be in the program counter when I type Control T again? 0, 0. All right, very good. So we'll do a Control T, and sure enough, it is back to 0, 0. Which means, when we are getting back to the fetch cycle again, it's going to go back and say, haven't we done this before? Yes, this is how we started the whole program. And that's why this is an infinite loop. It just does not end. Do we have any questions about the execution of this program? Do you guys want to see what happens in Logisim when we have an infinite loop? It's nothing really interesting, but I can show you anyway. So we'll go ahead and change the tick frequency to something that's more visible. 64, 32, 16 is definitely visible. And then I type Control T on the keyboard. And this is it. I mean, you can literally see the program counter. You're switching between 0, 0, 0, 1, 0, 2, and then back to 0, 0. But you can also see how the location being addressed in RAM is really just also cycling between those 3 locations. So that's basically, an infinite loop. It will never end. Are we doing okay so far with the demonstration of the jmpi instruction? Okay, great. All right, so I'm going to do another Control T so that there's no need to keep this running. So the next topic, okay, let me switch back to Joplin. And Joplin is right here. So the next topic is to talk about the flags in the ALU, the arithmetic and logic unit. So we'll go to the Logisim first, okay? And this time I will show you a trick that some of you may actually use during the lab, which is to open the ALU by itself. So even though the ALU was being used as a component inside the processor, you can play with it by itself too. Now, while it is a component inside the processor, you can't really play with it. In other words, you cannot change the input, you cannot change the operation select, and just to test what it's going to do. Okay, but now that I'm running the ALU or I'm loading ALU by itself into Logisim, it is just a little circuit that I can play with. Okay, which is handy. So the first thing we want to kind of recapture from the last time that we talked about this concept is that these demultiplexers will basically send in1 and in2 to the various operations that we can perform. This one is a little bit different. Okay, this one does have the multiply and the divide, but there are no opcodes to make use of those 2 operators. So don't worry about this because it's useless. Okay, there's nothing that we can use to map to those 2 operations. So those 2 are useless, but we do have the adder here that can be useful, the subtractor, the right shifter. This is the bitwise not operator. This is the bitwise and operator. This is the bitwise or operator. So all of those are in place and they're useful. Specifically, adding and subtracting are particularly useful, so we'll talk about those. This is the adder right here. So can someone tell me what OP or operation select needs to be as a 3-bit number if I intend to add in1 and in2 together? 0, 0, 0. Very good. Okay. So you can also see, how there are 2 tunnels, one tunnel from each one, the adder and the subtractor. One is C, okay, coming out of the adder, this tunnel here, and then the other one's B coming out of the subtractor. They are corresponding to, if you just hover over here, the carry out of the adder and also the borrow out of the subtractor. So if they are, in a tunnel, or if they're connected to a tunnel, they're most likely used somewhere else in a circuit. I use a tunnel here so that I don't make the design too busy. So you might want to keep that in mind. And then the other thing you also might want to keep in mind is we also have a tunnel right here called S1, another one here that is called S2. So what exactly are those? Those are the sign bits. Very good. Good job, because they are each corresponding to bit 7, which is the most significant bit of in1, and then the other one is corresponding to the most significant bit of in2. So they are basically the sign bits of the 2 inputs, to the ALU. So why do I want to keep track of the sign bits of the operands? What do you think I possibly will need those for, based on what we have already talked about in terms of the flags in binary subtraction? Go ahead.
That there's a carry bit.
There's a what?
That there's a carry bit.
Well, the carry bit is separate. Okay, so you can see the carry bit has its own tunnel. So the carry, the borrow have their own, tunnels. This is separate. These are just really the sign bits of the 2 things. Yes. And therefore overflow. Very good. Okay. So that's a very good, observation. Both of these, S1 and S2, they are for the calculation of the overflow flags. Okay. And do you guys still remember the overflow flags? Okay. It's trying to detect whether the sign of the result makes sense or not. Okay, that's basically what overflow is. So if you do want to find out how they are utilized, you can click on the node using the poke tool. And because that automatically highlights everything that connects to S1 as a tunnel. So when you look through the entire circuit, you'll find that, oh, so that's how S1 is being used. So S1 is being used as the input to calculate these 2 outputs here. Now you can also see that there's a multiplexer here to go to O out, which is overflow out. Okay, and you can see that for operation 0, it connects to this circuit. For operation 1, it connects to the circuit right below that. And then for all of the other operations, which are neither addition nor subtraction, overflow makes no sense. Okay, because when you're bit shifting, there's no such thing as overflow. If you're doing a bitwise AND, a bitwise OR, or a bitwise NOT, overflow does not make any sense. So in all of those cases, the overflows are really just coming in. We're just copying, okay, what was the previous overflow. We'll just preserve that. That's all we're going to do. Okay, so this particular multiplexer, just like all of the other multiplexers and demultiplexers, have exactly the same select bits. So if you look at the gray dot here, and you track down this node, they're all going to connect to exactly the same OPSEL that we saw earlier. So all of these multiplexers and demultiplexers are synchronized based on what operation you have selected. Are we still doing okay so far? Do you guys recognize, this is actually how we define overflow in subtraction? X has, let's see here. So you can see how this AND will become a 1. The X has to be different from, or I should say the sign bit of X has to be different from the sign bit of the Y and also the sign bit of the difference. So you can see there's a bubble here, but no bubbles over here. Or the other way around, you have no bubble here, but bubbles over here. So they are basically representing exactly the same logical expression that we have used to calculate overflow in the case of a subtraction. Yep. Yes, bubbles mean negation. And this is one thing that's really great because if you click on, if you use a select tool to click on the AND gate itself, it gives you the option of negating specific inputs. So that's why, because without this, we can still use like a NOT gate, but it's going to make the design a lot more, busy. This makes the design look a lot simpler like this. Yes. The NOT is in the input. So this is negated, this is negated, this is negated.
Like the circle is after.
Oh, right. So instead of using this mechanism, I could have also used a NOT gate. That is correct. I could have done that too, but that's going to make the design more busy. And this makes the design a little bit more concise. But they would have accomplished the same thing, yes. Yep, okay. So what about addition? Why do I care about overflow in addition? Because you can. Okay, so if we think about just using 4 bits, okay, so can someone tell me what is the smallest value we can represent using only 4 bits? -8 is correct, okay? -8 is the lowest or the most negative value that we can represent, and then the most positive value that we can represent is 7. Very good. Okay, so -8 to 7. So the question is, what if I subtract 1 from -8? So if I subtract 1 from -8 in binary, I will get the representation of 0, 1, 1, 1, which is the representation of 7. But the sign does not make sense, right? So that's how we can determine, that's how we decided why in subtraction, this is what we want to do it, how we want to do it. But in addition, what is going to happen? What happens when I add 1 to 7 for 4-bit numbers? What's going to happen? 7 is 0, 1, 1, 1, okay? 1 is 0, 0, 0, 1, that's pretty easy. What happens when I add those two together as 4-bit numbers? I get 1, 0, 0, 0, which represents -8. Does that make sense to you? You're adding two non-negative values and then you end up with a negative value. The sign doesn't make sense, we have an overflow. That's exactly what this logic is trying to say, okay? You're adding two non-negative values and therefore the sign bits are all zeros. And somehow the result has the sign bit being 1 being a negative value. We have a problem. And this line here will light up. Is that okay? All right. So we also have the L flag. So how did we define the L flag when we talked about binary comparison? Go ahead.
Exclusive or the overload and the S.
Yep. The S is basically the sign of the result of the operation. And here we have exactly the same thing. So when you look at the sign flag and the overflow flag, the sign flag, by the way, this thing here connects to the most significant bit of the result of the operation. So we have exactly the same definition here to define what is the L flag. So the L flag is defined even for addition, even though it doesn't seem to make sense. It's simply because it's a simple logic here. It's just an exclusive OR between the sign flag and the overflow flag. So I just decided, we'll just go ahead and compute the L flag accordingly. Yep.
What does the E mean there?
E means error.
Okay.
So normally it is a bad thing, but in this case, it's not so much a bad thing because in this case, the E is basically saying, I don't know what it is. Now, you might ask, why can't the logician know what the zero flag is? Okay, so in order to do that, we track it down. Okay, so we use the poking tool and we track down, where is Z out connected in this entire circuit? So we search and go like, oh, okay, this is where it's connected to. It is the NOR of all the individual bits of the result of an operation. So that means if the result of an operation is non-zero, which means there's at least one within all those 8 bits, then the or without the negation is gonna be a 1. But since I have this little bubble here, this is a NOR gate, which means it turns that 1 into a 0. The only time the Z flag is gonna be a 1 is when all 8 bits are 0. In other words, when the Z flag is a 1, it means the result of an operation is 0. Is that okay? So I have just basically explained here all the 5 flags that are coming out of the ALU. So the question is, great, so we have computed all of these flags. Where are they going to? They're all going to the flags out port. So the flags out port, there's a specific order. The carry bit is bit 0, the Z bit is bit 1, the sign bit is bit 2, the overflow bit is bit 3, and then finally the out flag, which actually does not have a name here, is bit 4. So those are the 5 bits that we output to flags out as a port. Are we still doing okay so far? Okay, there's one more thing I need to explain because you can see the C flag or the C tunnel is here, the B tunnel is over here. So remember, the C tunnel is coming out of the adder, the B flag is coming out of the subtractor. So this multiplexer in return is going to decide, oh, did we just do an addition? Because if that is the case, the carry of the adder becomes C out, which then connects to bit 0 of flags out. Or did we just do a subtraction? Because if we just do a subtraction, then the borrow tunnel becomes the output of this multiplexer, which also connects to bit 0 of the flags register. So the flags register is just going to be overwritten by the last operation. It does not keep track of a carry for addition and a borrow for subtraction separately. They basically merge into the same thing, the same bit in the flags register. Are we still doing okay so far? Okay. So one thing you can do, for today's lab is there are certain questions that will ask you what happens for this particular subtraction and what happens to that other addition. You can indeed just use this thing here. Punch in the numbers that you're supposed to be adding, specify the add operation, turn this thing on, and then get to the result. This is the actual result. But if you need to know the flags, those are your flags. Now, it's great for today's lab because you can be using a computer. But if you don't know how to do this by hand, it won't help. This is not going to help you in exam 2. Because in exam 2, it is all paper only. I mean, you can bring the circuit diagram of the ALU, but you still need to know how to read and interpret the diagram in order to answer questions. So I would suggest, unless you're really running out of time in the lab session, try to do this by hand. You probably still need to look at the diagram in LogicSim, but once you have the diagram loaded in LogicSim, try to figure out the individual bits using just try to do it by hand.
Would it be wise to print out the processor?
For exam 2, yes. Yep, you can print out whatever you want and bring it to exam 2. Yes.
So all the flags merged together and are outputted, and all their information on bigger.
Well, they become a 5-bit pin, so each bit here still has its own place, as the output. So now we're going to switch back to the main circuit. So in the main circuit, this is flags out. Okay, right here, this wire here, this wire is a flags out. So they go to the flags register, and the flags register will have will be enabled when the ALU is enabled, generally speaking. So that means, whenever you use the ALU, the flags register is going to update based on the result of the operation, with the exception of increment and decrement. So it's not important in today's discussion, but there's a special mechanism to turn off the enable of the flags register, so they actually will not be affected for increment and decrement, because increment and decrement are very important operations. that we wanted not to change the flag register. All right, so is all this stuff okay so far? Okay. And then what we're going to do is to switch back to the discussion of conditional branch instructions. That's in Joplin. So we'll focus on one specific conditional branch instruction, which is JCI. JCI is basically saying jump only if and only if the carry flag is a 1 to an immediate destination. That's basically what it's saying. So if you look at the RTL description, it is saying PC, the program counter, equals to, this is a ternary operation or ternary expression. The ternary expression is using C alone as the Boolean expression to determine are we going for the then expression or are we going for the else expression? The then expression looks exactly the same as a jmpi, which means in that case, yeah, let's go ahead and jump. Let's go ahead and continue execution as specified by the immediate operand. On the other hand, if C is 0, if the Boolean expression returns false, then we just want to say, just move on to the next location. Just continue execution as if the JCI instruction did not exist.
A quick clarification question. So
Yeah.
for JMPI, does the I stand for instruction as well?
No, the I stands for immediate.
And JCI is also, or is instruction?
It is also immediate.
Oh,
Yeah, the I is always immediate. So LDI is load immediate. JCI is jump if and only if the carry flag is set immediate. Because we are using an immediate operand to specify where we are supposed to go. In other words, where we are supposed to go should be determined by the assembler, or by the time we go through the assembly process, it should be known already. And you might suspect there's a variant of JC that doesn't have the I, and that is the case. There's a variant of JMP that is without the I, just JMP without the I. But in today's class, they're not relevant. They will be, one of those will be useful. JMP without the I will be useful when we talk about how to call and return, in terms of subroutines. But in today's lab and today's lecture, they are not particularly useful. So we're still doing okay? Okay, all right. So I'm gonna switch gear and take roll first before we move on to the conditional branch instruction. Yes.
Would it be useful to print out the list of
I would think so. I mean, it's probably only going to take one single page. So I would say, even if it's not useful, just having it can be, yeah, just having it available. Yep, go ahead.
When is the next step?
Now that we are almost done with describing all the instructions, I think next Tuesday, I will give you the practice exam or the exam from last semester. So that means your actual exam 2 is going to be 1 week after next Tuesday. Right, taking vote. All right. So this is where we get into, kind of really interesting stuff for this class, with all the branching instructions and whatnot. I distinctly remember that I put in 0330, but I probably forgot. All righty. So we'll go ahead and do it now. Von Neumann, bottom. So don't do it yet, until I say, go ahead. Oh, I also wrote a new module, but I have not unhidden it yet. So we can remember to do that. Okay, there we go. It takes a little bit of time to copy an activity in Canvas. All right, so this time it is here. All right. I think it was here already before. or not? All right, so this is 3-0. It is roll taking. All right, 15 minutes should be more than enough. And then I'm going to show you the passcode or the access code in this setting screen. Yeah, this one is long, it's conditional. All right, so let me go back and unhide the activity because you cannot see it yet. Unhide. You should be able to refresh your screen and see the roll taking activity for 2023-0330. Go ahead. That does present a dilemma, doesn't it? All right, so it will be 6:30 today. Okay. 6, there we go. Okay, so if you refresh again, you should be able to participate. The access code is conditional, all lowercase. While you guys are doing this, I'm going to set up, or actually I want to make sure the conditional branch node is indeed released. Okay, it is. And then we'll talk about how to assemble JCI something. In fact, since somebody brought up, whether it would be helpful to bring this particular opcode table, I would go one step beyond that. I would make a copy of the opcode table, and then you can put in whatever you want, as description or comment or whatever, or change the notation to one that you find more user friendly. Okay, all of this material is open, and you can make a copy of any spreadsheet that I have used in this class. All right, so are we done with roll taking? We good?
The access code again,
It's okay, conditional. Yeah, all lowercase conditional. All right, we are making pretty good time today. So that means I can show you some additional stuff that relates to the lab. The description is in the lab activity itself, but I think some people actually benefit from watching me do it once, because some people are more visual than they can read instructions. So I think that might be beneficial. Okay, so are we good, ready to go? Okay, all right, cool. So the JCI instruction is not that much different compared to the jmpi instruction, except it is a 4-4 in hexadecimal instead of 4-0 in hexadecimal. Okay, not a big deal. So now we switch back to Logisim, and we'll go ahead and reset this code here. Okay, so we'll go Control R and then change this location to 4-4. So once again, we still have quote unquote an infinite loop, but this is not really an infinite loop anymore, not necessarily. So what we'll do is to actually put a halt instruction here, because we might not branch back, okay, depending on how I set up the flags. Okay. And then somebody's going to say, but Tech, you did not do any subtraction or compare here. So who's going to change the C flag or the big 0 of the flag register? I can do it manually. Okay, I can always inject a value into the flags register prior to the execution of the opcode, so I can always do that later. So we'll go ahead and you'll fast forward until the program counter is 2, just like last time. So let me do that. So Control T until PC is 2. There we go. Yep.
So we're still jumping to 0, 0 if the C flag is 1?
That is correct. Yep, that is correct. Okay, so we are finally, the program counter is now at 0, 2. We are about to have a falling edge, which means we are about to have a decode. Okay, we're about to decode 4, but decode is really simple in this processor. All we are doing is copying the instruction register, which is the opcode, to the microcode pointer, but with a 0 padded on the right-hand side in hexadecimal. So there we go, 440. So the first thing we look at this, we look at here is to say, okay, I bet you it has resemblance to the jmpi instruction because, hey, after all, they are similar things, except this one is a little bit tricky because it can go in either direction. So we look at RAM first. RAM is indeed selected. We are reading from RAM. And if you look at how the address is routed, it is routed to the program counter just like before. So that part is the same, okay? The program counter is connected to the A port of RAM, and then the D port is a little bit tricky this time, okay? So what we'll do is we are going to look at things from the perspective of the program counter itself. In other words, we know the program counter will update because PCEN, which is coming out of the ROM data port, is a 1. So we know the program counter will update. The question is, how is it going to be updated? As it is right now, if you just look at the selector, but not to figure out, not to look into why the select is 0. So we are using input 0 of the multiplexer, which means it is coming out of the auto increment mechanism. In other words, as it is right now, and you can just poke the wire going into the D port of PC, it's going to change it to 3. Does that make sense to you? It makes sense because the carry bit, the flags register, just like any register, has a default of all zeros. Since I did not do a single thing to change it to a 1, the C flag is indeed a 0. And according to the instructions or the description that we saw earlier, if the C flag is a 0, we simply move on to the next following instruction, which in this case is a halt instruction. So in other words, it's behaving just like a jmpi instruction. No, I take it back. It is behaving as if it is not here. It doesn't do a single useful thing. Okay, so the question is, well, what if we change the C flag in the flags register to a 1? Because that should change the behavior, right? And we can do it now because the instruction doesn't do a single thing, or I should say the microcode and the processor does not do a single thing until we have a transition, in this case, a rising edge. So before the rising edge happens, I still have time to tweak it and change things around just to see, oh, if I were to do it this way, what would have happened? Okay, so that's exactly what I'm going to do next. So I'm going to change from bit 1 of the flags register to a 1, which means I type in 0, 1, and that changes bit 0 of the flags register, which corresponds to the C flag, to a 1. And the first thing we want to know is, hey, PCMux becomes a 1. It just became 1. It was a 0 before. So the next thing we want to poke is to say, which input is it using from the multiplexer? And that's the job of PCMux to decide which input of the multiplexer becomes PCMux. So we poke this node here, and it has 0, 0, 0 in it. So that means input 0 of the multiplexer connects to PCMux. So we track down input 0. Where does it connect to? Now this, I do apologize, this part does not look very good. So bit 0 is connected to this splitter. The splitter, after it is merged, connects to this node here. This is just for display purposes, okay? That's all it does. But it does come from the flags register. Okay, in other words, this particular mechanism with this particular multiplexer here, it is making use of the output of the flags register combined with PC-mux to determine PC-mux. And the PC-mux in return is going to switch between the two inputs to the multiplexer immediately before the program counter. And therefore, we now have a switch and go like, if it is true, go here. If it is false, go here. Now that we have doctored the carry bit to be 1, this PC-mux becomes a 1, and that means we're going to use this input. That input in return comes from this particular multiplexer here, which also has a select of 1, and that input 1 connects us to the D port of RAM, just like when I demonstrated the jmpi instruction. So this is how a conditional branch instruction happens in this particular process. I'm not sure about the other processors when I was trying to figure out, so how am I going to do the conditional branch thing? This was what I came up with. But do we have any questions about the mechanism? Yes.
So the condition itself was reliant on the carry flag being either true or false.
Yes.
Okay.
Yeah, basically the multiplexer that PC-mux comes to select is determining, are we just using a constant 1, a constant 0 for PC-mux, or are we using one of the 5 flags in the flags register, one of the 5 bits in the flags register? So that gives me the flexibility to say, well, sometimes we just want to branch all the time. Other times, depending, if I need to branch because the flag is a 1, then I do it this way. But if the flag is a 0, I just want to continue execution, and I just want to auto increment the program counter. So this gives me the flexibility of not only being able to decide which way, but also to decide who is going to help me decide which way to go. Question? Yes.
Operation immediately after the.
Because if I do not branch, then I would pause. I want the program to stop if I do not branch back to location 0. Okay, I can illustrate it. Okay, I can illustrate it because as it is right now, the program is an infinite loop because nothing in the program is going to change the carry flag to a 0, right? And I just doctor. Huh? Yes, I did. I injected a 1 to the carry flag myself. But once it's changed to a 1, nothing in the program is going to reset it to 0. So if I just do a control K right now, it behaves just like the jmpi program. It's an infinite loop. But watch this, okay? I can do things at the same time, or I think I can. If I change this flag to 0, 0, what do you think is going to happen? You will get to the halt instruction at location 03, and then everything just freezes, okay, it will stop. So let's see if we can do it, okay? So 0, 0, and we're done. So do we have any questions about this program? Yes.
It's affected by the flag. What is the flag doing? What is it doing the flag?
You mean what did I do or what the program did?
Yeah.
Which one?
What is the flag doing?
What is the flag doing?
It's
You mean this thing here? What I'm pointing to? It stores the output of the flags out from the ALU. But I'm not doing any arithmetic operations, so I just injected a 1 into bit 0 of the flags register. Normally, it would be storing the result of a subtraction, the flags after subtraction or after an addition. What it does is explainable by looking at the circuit. So that's something that I would highly encourage the entire class to do is, when you have a question such as that one, try to figure out the answer by analyzing the processor circuit, and if it has connection or if it comes from the register bank, or the ALU, then look one level deeper into those other circuit too. Because we have talked about all the basic components, the multiplexers, demultiplexers, RAM, ROM, registers. This is really just a massive connection of those more elemental components. So at this stage, you really should practice trying to explain how things happen inside the processor. Yep.
I'm a little confused by the jump thing. Those jumping to, like, let's say it was just the 5C was on still, it was jumping to the 0, then going to the 4, 0, and then jumping again back. That makes sense.
If the carry flag was a 1, when it was a 1, then we branch back to location 0, because that's what JCI0 is trying to do. Is if and only if the carry flag is a 1, branch to whatever the opcodes, whatever the immediate value specifies. But the moment I change the carry flag to a 0, then it's not going to branch anymore, which means it just goes to whatever instruction is after the JCI instruction. In this case, that's just the halt instruction, and that's why we hit the halt instruction, and then at that point, the entire program stops.
And then the PC will you reference PC. Can you explain that a little bit?
Sure, it's really just the reference operator, because we have RAM, right? And RAM is our memory. So this is the referencing PC, which means it's treating the program counter as a pointer. And whatever content is pointed to the RAM is used to update the program counter itself.
And that's what's causing it to jump.
That is what's causing it to change, yes. Well, one of the two ways for it to change when you have a conditional range. Because the other way, if the carry flag is a 0, then it's simply increment. It still changes. The interface is changing. It's just that in one case, it will change according to the immediate value that you specify as a part of the instruction. And then the other way, it just goes forward to whatever is next to, or I should say, whatever is following the JCI instruction. Okay. Yeah.
So PC is an address, right?
PC contains an address, or I should say, what PC contains is used as an address because it connects to the A port of RAM. So it's called a program counter, but it's also called the instruction pointer, depending on the architecture. So for those of you who might be working on the Intel architecture in the future, it is called the IP, which is the instruction pointer register. But other architectures tend to call this one the PC or the program counter. It's just a name. Are we okay so far with all this? But it is a counter. It counts, it's basically it's keeping track of what is the address of the next opcode that I need to execute. So from that perspective, it is a counter. An address is nothing more than a number. It's nothing more than an unsigned integer. So it is counting. Most of the time, it's just counting up until you hit a JMP or some kind of branch instruction, then it changes. Yep.
So in our case, for example, when we're writing these programs, we're starting at 0, 0, and then we're running through the program, and then it's jumping back to 0, 0, because that's how we made it. But for example, if we started at, like, the program starts at, say, 0, 5 instead, then it would still jump back to 0, 5, and it still treats it as a counter, but now we're starting at a different spot in memory rather than at the very beginning.
Yep, the best way to illustrate why PC is really just a counter is this. Okay, I can show you an example that I have shown before, but I did not mention it like this. So I just did a Control R, reset the entire thing. RAM is all zeroed out, which means they're all no op instructions, right? And then I just hit Control K, and your focus should be on the program counter, okay? And let me see if I can show RAM and the program counter at the same time. I can. So this is the RAM, this is the program counter, and I'm going to type Control K. In other words, I'm trying to execute the program that is null. It's all 0, 0, okay? So look at the program counter. I'll move that little finger out of the way. Can someone tell me it is not a counter? It's really just a counter, right? It just keeps counting up. That's all it does. But until it hits a conditional a branch instruction, then you can change the direction. Like, oh, where are we supposed to go next? Then you can say, oh, I want to continue execution over here. That allows you to alter the sequence of instructions that you execute. Are we good so far? All right. So we have just talked about everything that you need to know, about the processor, because the other instructions are just, calculation stuff, like add, subtract, and whatnot. They route the two outputs of the register bank to the two inputs of the ALU, select what operation you want to do, take the output of the operation, route it back to the register bank, and update one of the registers. Okay, and that's not it's something that you can track down yourself. So with only these types of instructions, we can now translate any C program. When I say C, I really meant C++. We can translate any C code into assembly code and have it happen in TTP. Yeah, I don't see anyone. Yeah, go ahead.
So I see what you're saying. So with the ALU, you said we don't have access to those multiplication and division operators.
Yeah.
So how would we do something?
That's a very good question. Okay, so let me pause the execution first. And we go into the ALU. I'm not even sure this one. This one does not have the additional ones. Okay, so, and I'm skipping one here. So we actually have 3 slots for 3 additional operations. Okay, never mind. That's okay. I'm going to look at this one here, which does have the extra operators. So I will need the microcode to specify 110 and 111 respectively, to specify that we want to multiply or divide. Okay, so I need to find one of the available opcode slots to say, hey, this opcode, this 8-bit number is going to specify the operation, but at the same time, I also need XXYY to specify, all right, if we are multiplying, which 2 numbers are we multiplying? If we're dividing, we have to specify which one is our dividend and which one is our divisor, right? And then it routes back, and then I have to specify which register is going to update to store the product in one case, and I can only store either the quotient or the remainder. I cannot store both at the same time for the division. So I need the opcode, but then I also need to modify the assembler so that I have to invent two new mnemonics so that the assembler would also understand, oh, so MUL is for multiplication and then div is for division. Yep.
But like any processor nowadays are way more than these opcodes, or is it?
Oh yeah, way more. Yeah, the TTP has what, 25? The last time I counted. So even with divide and multiply, we bump it up to 27. The Intel processor, as it is right now in the 64-bit format, has probably more than 1,000 instructions. Yep, it's not easy for a human to write code for that processor. Yep, go ahead.
Would it also need kind of corresponding construction in the ROM to be able to?
Yes. So there is first of all, you have to allocate the opcode. So in the opcode table, I need to track it manually. Then I need to go to the ROM and overwrite the specific location corresponding to the opcode with the microcode that will do the routing correctly. It's going to be very similar to add and subtract, with just the OP cell being different. And it will be a family. Each one is going to be a family of 16 actual opcode, because XX specifies 4 possible registers, YY specifies 4 possible registers. So I now have to specify 16 opcodes per mnemonic in the ROM, and then I have to modify the assembler to also recognize the mode MUL or mode, for multiplication, and div, for division are actual mnemonics. So there are a few steps, but they are not insanely difficult. Yep. So we can add, actually, we can add additional instructions, it's just that, you have to make a lot of adjustments, to make it happen. I mean, you guys can make a copy of everything and actually do it yourself. This is really a very DIY kind of processor. You don't need to pay a lot of money for a foundry to say, well, can you make my chip for me? Okay, we're going to charge you, hundreds of thousands of dollars, and we'll give you a batch of 500 processors. But I just need one. Well, sorry, we don't do business with people like you. This is all simulated, right? So you can make changes all you want, as long as you know where to find the original and re-download everything, you can play with it. That's actually kind of the intent, the original intent of doing it this way to teach this class is for people to play with it. It's like, I'm gonna download it and tweak it and, oh, okay, things don't work anymore. Fine, re-download the original, you're all good again. All right, so let me look at the time. We've got 10 minutes. So I'm going to talk about a very important topic in terms of how you debug your program. This is a it's only an introduction to how you can debug a program, but then later on we'll have much better tools for debugging programs that are written in TTP-ASM. Okay, so this is not going to be useful to me anymore. I'm just going to close it and we'll get back to the processor. And this time I will write a program that seems to be somewhat useful. So we'll go to the assembler, go to source, and this time I'll actually write some code that does something, okay? So we have LDI A with, oh, I don't know, make it 7, LDI B and give it 8, okay? And I'm just gonna use AND between A and B. And then we'll do a JCI to label L1, which is not defined yet, and then the assembler is going to complain about it. Yeah, that's appropriate because I have not defined label L1 yet. And we put a halt instruction here. This is label L1, and we'll put another halt instruction here. In other words, there are two ways for this program to terminate, to end. First of all, can you figure out which halt instruction is actually going to end this program? Is it the one on row 5 or is it the one on row 7? You have a 50% chance of getting it correct. But guessing should not be how you do this, okay? So the question is, are we going to branch or not? This is another conditional branch. It branches if and only if the Z flag is a 1. The Z flag is 1 if and only if the previous ALU operation ends with a 0. The result is a 0. So the question is, if I do a bitwise AND between register A and register B, one has 7, one has 8, is the result 0? So you have to think, what is the binary representation of 7? 1, 1, 1, having all the most significant, more significant between zeros. What is the representation of 8 in binary? 1, 0, 0, 0, right? So do you see any position being ones for both numbers? No. Okay, so that is the result should be a 0. So that means JCI should indeed branch to label L1, which means we should end at the halt instruction on line 7. Okay, so that's just a kind of tiny little test program. But what I want to show you is how do we keep track of the execution of this program for debugging purposes? So let me first download the RAM file first, and then I'll show you how to do this in Logisync. So we download as a CSV. I typically use CSV. You can use TSV if you want to. We'll call this one, JCI. because it demonstrates how JCI happens. And then we switch to logic sim. Go to RAM, Control R first, you'll reset the whole thing. And then we go to load image, and then we change this to jci.csv, and then we load the program in, okay? So if I were to type Control K right now, it will give you the answer because it will stop at the right place. But then you don't know how you got there because it's going to be going so fast, you don't know how you got there. So what if I want to look at the trail of the execution of this program? Well, the best feature that you can use is to go to simulate, go to logging, and now you have several ways to log how the program executes. Okay, because once you get there, it will give you this particular screen. So this particular screen has 3 tabs, and I have already configured something here, so I should probably reset everything. So I go to selection, and let me just remove this, okay? So the selection tab allows you to specify what do I want to log, okay? These are all things that you can log. In fact, you can go to RAM, which drops down, and you can say, if location 0 changes, I want to have a log entry. If location 1 changes, I want to have a log entry. So, but this program does not change RAM at all. So it doesn't make any sense to log RAM locations at all. Register A, B, and C, A, B, C, and D can also be logged. So when there's a change to one of them, you can log those. So of all of these things, which one do you think is relevant? If I just want to know what path the program took to get to the halt instruction. Program counter, okay? Because the program counter is indicating to the processor where the next opcode is, okay? It determines when we fetch, that's where we are fetching from, right? So the program counter seems to be useful, okay? So we'll take the program counter. So that means you just click on it and say add, which normally automatically use it in tracking in base 2, which is not easy to read. I would change it to base 16, in hexadecimal. That is okay, but remember the program counter also changes. It also increments right after the fetch cycle. And then for LDI instruction, it also changes. For jmpi instruction, it also changes because it needs to grab the immediate operand, right? So if you just crack the PC, you can get all the information in there already. But which PC corresponds to an actual location of an instruction or the opcode may not be clear to you. So what else do you think might be useful that we can use to say, yeah, we are fetching? It should be staring at you in the face right now. No. Op fetch. Because that tells you whether we are fetching or not, okay? So I'm going to add this one too. And this one being a single bit, doesn't make sense to turn it into base 16 because it's all going to be the same. Base 2, base 10, base 16, it's going to be just 0 or 1. So I'm going to log these 2 things, okay? We'll see what happens. All right, so the next thing is you can decide, do I want to track it as an internal table inside Logisim, or do I want to trace it into a file? I would recommend using a file because this way you can use an editor, you can use a spreadsheet to process it, okay? So I would recommend using a file. If you do decide to use a file, you can do a select, and then you can select, in the file, in the folder, what name you want to use for that particular TSV, tab separated value file. So I'm going to use jci.tsv here. Click save. So from now on, whatever the program does is going to leave behind a trail, and that trail is going to be stored in that file that we have just named. You don't have to close this window, you can leave it open. And now I can do a Control K, and program has reached a particular halt instruction. Control K to stop the whole thing again. Yes.
Formatting the file has to be.
It's not up to you to decide because it is a file that this program generates. So the file is now generated. let's go take a look at what it looks like, okay? So I will take a look at that file just as a text file. Or I can use a spreadsheet. You can even use Google Sheets if you want to, okay? But I'm going to use, do you guys want me to use a spreadsheet or do you want me to use a text editor? Either way is fine with spreadsheet. Spreadsheet, okay. So I'm going to use, do you want me to use Google Sheets or just a local spreadsheet? Google Sheets, okay, we can do Google Sheets. In fact, I can just add a new tab to the assembler for now, so I'm just gonna, I'll do this temporarily, okay, so I will remove this tab later on. So sheet 12 is going to be the import of that file. So I go to import, and I select upload, browse, get to the file that I just generated, which is called what again? jzi.tsv, or tab separated file, or tab separated value. And then you get to this screen here. I already got a tab, so I just want to replace the current sheet, not the entire spreadsheet, just the current sheet. And I already know this is tab separated, so I'm just gonna specify tab. And I'm gonna turn off convert text to numbers, dates, and formulas because Google Sheets does not automatically do it to hexadecimal number. So we do import, and this is what we get, okay. So how do we read this thing? Well, each row is representing a change to either the program counter or OP fetch. OP fetch is a 1 if and only if we are actually fetching something. So that means anything with OP fetch being a 0 is not relevant to us. Does that make sense? So we want to focus on only the rows with OP fetch being a 1. Okay. So now we can tell that we started off with location 0, then we move on to location 2. Oh, but what happened to location 1? How did we skip location 0, 1? Off fetch is a 0, but what is in location 0, 1 that we did not care when we just want to find out what instructions we executed?
The value we were setting to A.
That is correct, okay? Because at location 0, we have an LDI instruction. The LDI instruction has 1 byte to specify the opcode, but then it also has a 2nd byte to specify the constant that we want to put into the register. That 2nd byte is not an opcode, so that's why we are not fetching that 2nd byte. So by the time we are done with the LDI instruction, we are at location 02 already. Where do we go next? Location 04, same idea, okay? Because we had 2 LDI instructions, and then we get to location 05 because that's our bitwise AND operation, right? So it only takes 1 byte. No, 04 is where the bitwise AND is. 05 is where the conditional branch is. So after the conditional branch, we ended up at location 08. We skipped a whole bunch of stuff. Does that make sense to you? Because the conditional branch did happen, so we basically continued execution from the JCI instruction all the way to the whole instruction at label L1, and that's why we skipped all the way to location 08. Yes.
So that bitwise AND returns Z as 1, and then we just.
That is correct. Yep. Now, if that is your interest, and you say, okay, I want to keep track of the flags too, okay, there's one more thing that is really important that I need to let you guys know, but there was a question. Okay, go ahead and ask that question first. I thought, yeah.
Is the increment on the rows mean a rising and the change in edge? Like when.
Say that one more time.
Because there's like, when one on the row.
This one here?
On the row of the spreadsheet for both columns, does an increment from 1 to 2 mean a change in edge?
No. No, because the clock itself is not part of the things that I track, because otherwise we have a lot of entries I don't want to deal with.
Then what part of that is?
I'm keeping track of OP fetch. It's not the clock. It is not based on edges. OP fetch is a pin in the circuit. So if
I
you,
mean, like,
In every line, one of the columns change. But if the one column doesn't change, the other one did.
It will only create a new row in the log if and only if at least one of the two things that I'm tracking changes. Right, okay, but what I'm going to talk about next is also important. So let's just say that you want to run the program again and you want to trace it again because you did some changes. So if I go back here and I go back to this particular screen, if I don't do a single thing and I rerun the entire program, the new log is appended to the file, which can make things very confusing to read. Okay, so if you want to reset the file and go like, okay, forget about the old log that's already here in this file, I just want to restart the whole thing. This is what you need to do. This is really important for the lab today. What you need to do is to reselect the file. It can be the same name. It's not a problem. Click save, and it will tell you that the file already existed. The default behavior is append, but in our case, we want to do an overwrite because we don't want the new log to be appended to the old log. So otherwise it will look confusing. So we just click overwrite. So now if I run this code again, you'll reset the whole thing, run the code again, then it will give me another log, but it's from the beginning. Yep.
Is that a one-time thing that we do? We click overwrite and then we can rerun it as many times as we want, and it'll overwrite the file?
No.
We have to reselect it.
You have to reselect and specify overwrite every single time. The default behavior of your rerunning, because it doesn't know that you're resetting things and trying to run from the beginning. So every single time you continue to run something, it will end it. Yes.
And we would have to update as well.
It depends. I mean, I used Google Sheet for this purpose, but you can use Excel at the lab. You can use, I mean, you can use the text editor. It will be obvious in the text editor.
Yeah, doesn't typically like much user, they will just like update every time.
I think so. Yep. Okay, and the access code, you need that too. So let me, yeah, I know there are a lot of things that we need to talk about. So the lab is called Simple Branching and Code Analysis. And then the access code is JOY, J-O-Y, not J-O-I. It's a play of the word.
So J-O-I.
All righty, I'll see you guys at the lab.